Thank you very much. Can you hear me here? This is on Monday. This feels like a Friday meeting with the client because there's cracks in the project. There's a lot of people, so that's awesome. But I'm going to be talking about contractors execution, means and methods, and obviously how we can reduce cracking. However, I scratch it because it's a question. So the question is truly, can we eliminate cracking as contractors? Or truly all we can do is mitigate, reduce, control, and all the things, right? So I kind of adjusted the title there. Presentations before were great because I think they touch on the same points we all touch in. Communication, integration, it's a group effort. There's a lot of nonsense out there. Shrinkage testing is something that obviously is coming through more and more. And obviously, as you're going to see in a minute, my perspective is very different because what you have heard a lot is more on the building side. That's where you see most of the cases in ACI. My perspective is obviously different. So you can see this is the type of work we do. So rarely doing a lot of, just high-rise buildings. We do a little portion, about 5% of our work is buildings, but most of our work is infrastructure, and obviously very different to the perspective you're going to see. So imagine if I get the crack sizes that you were talking about before, good luck. We'll be very happy. We're typically talking about 0.006, 0.004 cracking type of issues. So it's very different, the type of challenges you see in the building side versus the infrastructure side, and obviously the type of clients you're dealing with are very different because we typically have government clients, federal clients, highway authority, bridge type of clients, marine type of clients, Navy type of clients. So the expectations are very different than a traditional private client that you can negotiate things. So. Obviously, the other challenges we have is the work we do is not just, a high-rise building. We need to take the concrete from point A to point B, and typically the challenges are not the same. Although you can be in New York and have very difficult challenges for placing concrete up. We sometimes have to barge concrete. You have to pump concrete in the river or in the ocean. We sometimes obviously have to deal with the type of rebar you see here. So when you see research, I'm going to mention it later too. But when you see research talking about cracking and slump, and they tell you that you cannot exceed 4 inches slump for improving the cracking of bridge decks, well, I think that, obviously that's not going to apply for most of the work we do because good luck trying to put 4-inch concrete in that type of rebar, right? So you start making sense with and challenging the research that we have to read sometimes in ACI because it doesn't make any sense. And the other part is obviously we have different expectations of construction. When you see a type of work like segmental bridges, you need to be dealing not only with the precast work and quality and the cantilever balance that you do in a segmental bridge, but once you go then to connect the bridge, then you obviously need to deal with a very high early strength concrete mix, need to be flowable, heavily reinforced, and then you need to control the cracking that is going to form from the shrinkage and restraint conditions and then the thermal cycles you do before post tensioning. So very difficult situations we have there to control cracking, but it's part of what we do. The other perspective on challenges is also specs. So this is a slide I've used in several of my presentations, but it sends you the message very clear in one snapshot, okay? Sometimes you have clear goals, but they do not have properly defined requirements. So good luck, for example, if you see there, dimension, stability, and freedom from cracking. What does that mean? What does that mean? Because that means a lot of things. Okay? And if you don't put a requirement to specify and control and limit the way you're going to measure, what are the metrics to actually analyze and measure that requirement, you're going to be in trouble. The other part would be hidden goals, define requirements, so that you get in there into the prescriptiveness of people thinking that there's one way of doing things. Many times you see that for people that actually stay just in their own state, in their own city, in their own town, and don't get out of there. If you get out of your town, you're going to realize that concrete is very different everywhere you go. Actually, you were talking about shrinkage. There's no good number because depending where you go, 0.05 shrinkage is great and 0.03 may be great in another part of the industry, and the aggregates you have locally cannot allow you to have very low shrinkage in some part of the United States. So again, there's no magic number, but we get the false impression that concrete is just one size fits all and you can make it work. So then you get a requirement like the bottom there. What do you think is the message hidden in that requirement? They're forcing you to use a certain amount of aggregates, a certain combination of aggregates. The owner wants a low shrinkage mix. They don't want to have a mix with a lot of paste, with a lot of mortar, that is going to end up to be actually then, shrinking, like Calvin mentioned. What shrinks? The cement paste. So they're trying to control that indirectly by forcing you to have a certain mix, okay? But then you deal with the issues of reinforcement. As we know, reinforcement continue to increase with today's designs because we have additional requirements in the codes, additional concerns for different exposure conditions and loadings, and then we see more rebar. But then we still maintain these prescriptive requirements, and those are not good for construction. And then as I'm looking at all that, this is also, I'm being part of a lot of initiatives for productivity and constructability of specifications for concrete. And I believe we sometimes try to engineer too much the approach to specifications. And if you kind of step back and look at what we have learned to set goals, to truly set goals for us, right? Even in the management side as a person, as a professional, a smart way of setting a spec is pretty easy. Because when you think about it, you need to be very specific to what you're requiring, right? You need to make sure that you have a measurable way to assess that. You need to make sure it can be achieved to the point that we're talking here. Can it be achieved? Then it needs to be relevant to the work, to the point that actually, the previous presenter speak. If the crack doesn't matter, what do you care, right? And then time bound, right? So there needs to be a time bound limitation too. Because if you get a crack after the structure is in service, that crack formed most likely well later than you build the work. So now why the contractor is responsible? A crack that happens that late is actually a design issue, not a contractor issue. You understand what I'm saying? So why would you actually have then all of a sudden the contractor trying to fix a crack that happened 3 years later when the design should have actually been addressing the long-term cracking issues that could have occurred? So again, it's understanding how we develop specs is extremely important to make sure that we have the right solutions in front of us. Okay? And this is actually, if you are not going to take anything from this presentation, pretty much this is your snapshot of the presentation. I always like to show a little bit on the front and make sure we close on the same topic. But pretty much what we're saying is this is not a one-person solution. Okay? This is not the designer coming with the best design. Because what happens if then you get the worst contractor and you have a bad mix, right? What happens if you have the best contractor, the best concrete supplier, the best designer, all of them put in their best effort, and the client doesn't want to spend the money? Contractors, designers, producers do what we're paid to do. If you're not getting paid to do something, why would you do it? Why the owner doesn't want to spend more money? It's important to understand that we are dealing many times with cracking because that's what was bought. To the previous presenter's theme. They bought something, but nobody told them that actually what they bought is actually a different type of project. It's extreme. I always say, I think I agree 100% with Calvin, I agree 100% with the design perspective, but what I believe is extremely important is that we realize there's nothing wrong with having a difficult conversation at the beginning. There's nothing wrong with going to that owner and saying, Mr. Owner, these are the alternatives we have in front of you. We have these alternatives that have some cracking issues, and we have an exposure condition that is a concern. I believe we need to address that. Or no. Or just talk about, we have this cracking, we believe that cracking is within the standards, and actually if you see cracking as we start building the work, that's within the design expectations, right? And see what happens at that early stage. Again, to Calvin's point, well, most likely the owner is going to be stubborn, it's not going to make the decision. But you know what's going to happen? The next one is going to come and build it, it's going to get cracked, and it's going to have to deal with that. That's more expensive. So again, it's a factor of the group involvement, and make sure that you get to that middle. Now, you get to that middle, there's no guarantees on no cracks, but certainly can you maybe reduce the crack once you get to that middle point and agree on the approach to actually get the solution. So obviously we'll go here a little bit on the step by step because it's important to understand construction, and what I'm going to be showing, I'm going to have obviously less text as you're going to start seeing my presentation, it's getting more figures and photos. But certainly there's an aspect of strength, durability, workability, and economics. Once you approach any concrete project, you need to understand there's a balancing act. It's not all about, we got a crack, and then what? If you get a concrete mix that actually is very low shrinkage, that has very good aggregates and all that, but you cannot place it, well, that's worse, because now all of a sudden you're going to create a lot of voids, consolidation issues, and then there's going to be obviously no ability to develop that strength. So you need to make sure you balance the approach to concrete. As we all know that, the other thing is, what is the schedule in front of us to develop that solution? If you are going to a commercial, concrete producer, and he doesn't have the solution for you to get a low shrinkage or get a low risk of cracking in the mix, that's going to take time. And depending on the type of work you have, that's going to likely be obviously another issue that you're going to have as you start building the work. So make sure that you understand what is that in front of you. For the concrete producers, putting an admixture is not going to solve your problem. We continue to see, well, let's put an admixture and that's going to make it. You need to develop the good mix. First, make sure that you have a mix that have good quality materials, you optimize the water demand, you reduce space content, you reduce mortar content, you optimize it for the purpose of the work. Then, the admixtures help you enhance that performance for whatever application you're going to have. If you have a bad mix, and you try to put admixtures, it's going to still be a bad mix, but it's just having a lot of different admixtures. And then the economics. Many people misunderstand economics of concrete. And many people believe that contractors think about, give me the cheapest mix. The cheapest mix is not the best solution. I'll tell you that. And you can say a contractor said that. The cheapest mix is not the right solution. It needs to be a mix that is optimized to do the work that you need to do. Talking back about architectural concrete. Let's assume that you have an architectural concrete mix. And it gives you a beautiful finish. But it cracks. How good is that? You still have a bunch of cracks in the architectural phase, and now you have to deal with that, right? So make sure that you understand, as a concrete producer, some of you ask the right questions. Don't try to get into the cheapest solution. So I know we have a competitive market. We get it. But it's not necessarily the cheapest. Maybe you need to go a little bit higher, sell the value of the mix, educate the concrete contractor and the owner to make sure you get the right solution. Okay? And the other part that I want to talk about, lubrication. Lubrication is extremely important for construction. As you saw, the type of work we do, sometimes you have to pump concrete long distances. You have to obviously, take it into different, ways of transportation. And obviously you need to have that concrete workable. So I always make sure that people understand concrete from this perspective. There's 3 levels of lubrication. The first level of lubrication, what is? The water, right? What happened next? You get the paste, and then you get the mortar. The 3 of them need to be balanced, right? If you have a mix with low water, you're going to have a poor quality paste. If you have a mix with low paste, you're going to have a bad quality mortar, right? And if you have a low mortar, you're going to have a bad quality concrete, right? So it's a balancing act of how you approach concrete mixes. And all that is here, because to build work, you need to actually have different levels of lubrication. I didn't come with this. If you go through these references, CA and ACI, you're going to see that different type of applications require different levels of lubrication. Okay? Okay, so let's talk about cracking. And I'm using this for reference in respect to Dr. Darwin. I believe that he has done a lot of good work on bridge decks and all that. But I think he make a point here. There's a lot of different aspects of concrete work that actually is impacted in bridge deck construction that can result in cracking. So let's go about, one of the aspects that obviously we deal a lot, and then I'll talk now about construction efforts and means and methods. This is in hot weather. So what do you think happened here? We got rapid evaporation of the surface and created 2 issues. And I'm actually putting tearing as part of the disruptions of the surface, although it's not cracking, right? That's why I put a question mark. But what happened here? As a builder, what you did not do? Well, you did not likely protect the concrete correctly during the time of construction, right? And you allow it to be exposed and lost moisture on the surface. So what's going to happen now? In the first phase, what's going to happen first? You cannot finish it well, and you're going to tear the surface, and you're going to break that surface, and then it's going to look like that. It's going to have an issue with the surface quality. And then what is the other issue that could happen in the plastic state? You're going to end up with all the plastic shrinkage cracks. Okay? And that plastic shrinkage cracks typically tend to be limited to the top. However, with time, what's going to happen in some cases is that eventually with time, drying shrinkage comes and compounds to those cracks and get a little bit deeper. Okay? But that's a responsibility of the contractor to protect and cure the concrete in a timely fashion. Okay? Sometimes what's happening, and I'm not going to blame the contractor 100% on this one, but then you get mixes that have low bleeding. But then that's why the concrete contractors need to start understanding concrete materials. And I believe what's happening right now in the industry with a lot of the discussion that we're seeing in the change of 1L cements and contractors and concrete producers and all that, is that we have been used to actually having a certain type of material for a long time, and now with the change we realize that we need to get more involved. We as concrete contractors need to be earlier involved. We as designers need to be earlier involved. Bring those contractors to the game. Bring the concrete producers in front of those designers. So you understand how you can specify correctly. The concrete producers understand how to design mixes correctly, and the contractors know better how to actually use the mixes available to build the work. Right? But what's happening now a lot is people are claiming that there's low bleed conditions in the newer mixes and all that. Well, you know what? Work with the concrete producers to develop a mix that works best for you. And do the test, do the trial, check how the mix works. If you have to make modifications, work at it before you go into construction. And that's how it looks. I actually have it embedded there. That's how it looks at cracks, plastic shrinkage cracks. So many people have never seen it. They believe that it goes deep. In this case, it's pretty shallow. What about this crack? I'm going to show it here and let you figure out what happened here, because obviously it's pretty easy, right? What do you think happened? You see the crack here? You see there's another crack here? Do you think that crack was caused by, in this case, this element, issue during construction? Or do you think that there is here already an existing crack or disruption in the surface that is actually reflecting the crack on the top, right? How can you control that? Because you did not design it, you're building the work, you have that you have that interruption of continuity on the bottom of the substrate surface. All of a sudden you build it exactly to the drawings, exactly to the specs, and you get a crack there. Who's responsible for that? Well, eventually it doesn't matter. You're the contractor, you're going to have to eventually fix a lot of things to make the client happy, and eventually that becomes a negotiable point. But you need to have those, as designers, you need to have a better understanding of the site. If you have conditions on the site that are going to create that condition, and actually they fall even in a bearing surface, what do you need to do? Is there a detail in your design of drawings to actually modify that location, to disrupt the concrete element, to make sure you don't get those reflective cracks? And then I'm going to read you here about, this is actually coming from Europe. I'm not going to make you read the whole thing, but on the bottom, it says, if the concrete does not crack, then the reinforcement is not being used effectively. Okay? Then it says, when the specific performance requires cracking to be avoided, special measures are available. But this may have significant cost implications that the client should be aware. Again, in Europe, we have this in the standards, recognizing similar to what we have in the ACI documents sometimes that we talk, cracking is expected, just be aware. Okay, so for mass concrete, we have those type of documents in Europe. It's actually a very good reference for all of you doing thermal control plans too. And this is an example of we were doing a spillway work in Canada, and we ended up with a situation actually that showed some cracks in a mass element. And there's some locations that you may see in the corner here that could have been actually caused by disruption of the surface protection and all that. But what I want you to focus is with these geometrical cracks. These cracks that actually start showing, to actually start disrupting the flow, the continuity of that element. That's not a surface gradient crack that we're trying to control with the thermal control plans. That's not. If you don't know, thermal control cracks actually, based on the standards in North America, are not intended to control those type of cracks. It's obviously a misunderstanding, I would say. Because the cracks that you're trying to control are the type of cracks that you have here on the edge. These cracks here on the edge that are very random, and I just marked some cracks, I couldn't mark all of them. Those cracks are related to loss of surface protection. You create a thermal shock, you crack like a glass, think about it that way. But these are mass gradient cracks. Mass gradient cracks are associated to the thermal contraction of an element. Thermal contraction of an element is not about the temperature difference, it's actually from the temperature drop from the maximum to the equilibrium temperature. And that's what you see here. And this actually happened much later after we have built it and already have a lot of work completed that is starting showing up with time. And you can see here, they show vertical. They show exactly like a drying shrinkage crack. Because instead of drying, you're getting thermal contraction. So it's a mass gradient, a complete section actually just contracting, and then you get the cracks. These cracks are not construction cracks. Those are design cracks. Like it or not. The designers need to design for mass gradient cracks. They need to have the right amount of reinforcement. They need to have the right amount of temperature limits. And then they need to do a design to properly understand the effects of restraints and the impact to sequential construction in the process. It doesn't matter how much you can actually cure and protect the concrete within the temperature limits specified. You can keep it below the 35-degree differential. You can keep it below the 160. You can use the right mix. This thermal contraction is going to occur. It's a massive element. If you don't put the right amount of rebar and you don't control the maximum temperature, the material is going to have a certain, obviously, loss of it's not going to develop the tensile strength to tolerate that. So you're going to have to protect it. Okay, this one is interesting. Many people have seen this type of cracks, I guess. Or at least this is a type of crack we talk a lot in ACI when we talk about, cracking. It's plastic settlement cracks. How many of you have seen plastic settlement cracks before? What is the main cause of plastic settlement cracks? Just assume. There's no right or wrong answer. Just tell me one. On the left side, what is the cause of plastic settlement cracks? Too much water. Why too much water? I'm going to pick on you, whoever said that. Bad makes design. What happens if you have too much water? That's one cause. But tell me, what is it? Why do you say that? Why do you say that too much water is a problem? Okay, so you may have a lot of bleeding and you may lose the viscosity of the paste and therefore you settle. Okay, that can be a cause. Great. What about on the right side? What else could be a problem? Plastic settlement cracks. On the right side. High cementitious. Okay, how would you cause that with high cementitious? Okay, got you. So you say high amount of pozzolanic material that then delay the setting or something like that? Is that what you're saying? Okay, got you. Those are potential causes, right? But some of the claims, and this is where I want to bring this here, some of the claims is that obviously high slump obviously can cause that. And that has been perpetuated in research and continues to be a problem in construction. Because as I show you, when you have a lot of rebar, you cannot limit the slump. All of a sudden, how are you going to build the work? And if that was the case, then you get the same type of cracking in SCC, and then all the SCC mixes will be full of cracks, but that doesn't always happen. I'm going to show you one that has it, but that doesn't always happen. So the perpetuated research obviously showed different effects. It talks about bar size, it talks about slump, it talks about cover. There's other impacts in research, but certainly one of them is uses low slump concrete is also recommended to prevent settlement cracks in bridge decks. So the intent of that is actually that if you, in the past, right, remember slump was managed with water, so the higher the slump, more water, to his point, and then the more water, then you dilute the paste, and then you create a lower viscosity, right? To improve, obviously, the resistance to plastic settlement cracks, you need to have, obviously, higher viscosity, because then you don't have the effect of settlement of the mix, and then everybody stay happy together in the same place. Okay? But what happened again with this? How do you do a 4-inch concrete in this type of rebar, right? How do you do that? It's not an easy way, because you will not be able to do it. So when we deal with this continuous research that talk and correlates slump to durability or cracking issues, we continue to have, obviously, some conflicts in the industry trying to build work. And then what I'm saying is the clients, the people that are not here sometimes, get misled and misunderstand the concepts. And all they go and say is like, yeah, we need to have a low slump concrete for your bridge deck to be free of cracks. Well, good luck, because then how are you going to build it then, right? And obviously this is a case that happened, this is a project actually that got into a cold weather situation by a cold front. So the top surface got frozen. That's why you see the quality of the surface is actually damaged. And then when we did the cuts, we saw a lot of the cracks that typically happen on as a result of plastic settlement. In this case, it was more of a plastic settlement because the mix was not setting for a long time. The cold weather came, was not protected, it was without setting, so it stayed long time without setting. So you have a plastic condition there, and you ended up settling on top of the rebar. Now this one, what is it? Because then all of a sudden you have a low slump condition, but you have a mass concrete, so it talks to the point that you brought earlier about high SEM replacements. When you have high pozzolanic material there, when you low temperature, then it takes you longer for the material to set. And then by not setting, the same effects happen. And in this case, it's magnified because you have a thicker section. It's a mass concrete section, so imagine the mass section obviously settling on top of that rigid rebar, and then you get those type of cracks. So both of them can happen. They can happen in low slump concrete. They can happen in self-consolidating concrete. So it's not necessarily the slump what matters, but actually the material you use, the conditions of the temperature that you use, the level of stiffness you have in the rebar system. Even if when you have a lot of rebar connected together, you don't get that effect, because all of a sudden you're bridging across the rebar. But if you have just one rebar here and 12 inches, you have another rebar, then you create like a sack, like a hammock, right, condition, and you can see a bigger effect of that. Now, what do you think happened here? I'm going to let you see that. So this is about restrained shrinkage cracks. If you see that cross section, what do you think is the biggest problem with that cross section? What is the misleading detail on that cross section? You see some, if you can read from there, you have a socket and you have welded wire mesh. What do you think is going to happen to that socket? Somebody's shaking the hand there. What does that mean when you're shaking your head? It's an architectural detail. It doesn't do anything. You're just scratching the surface of a system that has reinforcement crossing through, and the socket is only like this. It doesn't get deep enough to create a cut. So you're just making a little nice reveal on the surface that make it look nice for you, but once it starts cracking, it's going to crack all over the place. Right? So in this case, to make it work, what you needed to do? Make sure the design provided a nice socket deep enough, right, to make sure that that system is going to get dislodged there and discontinue the welded wire mesh on that location. So you don't have continuity of the rebar there, of the mesh in this case, right? So you allow the system to pretty much break there. Okay? So we got in a case like that, and we obviously presented to the client all this, explained to the client, it's a federal client, so we obviously explained to the client that, the design they have in front of us didn't make sense, that all the remove and replace they were asking, was not necessarily, in alignment with the specifications and the design. And to Calvin's point, he mentioned that he has never seen anybody doing this cracking analysis to actually, by any designer, which is true. People don't do this when actually you're designing. You actually start using this when you have a problem and you have a design team, that has the capabilities. So this is what we end up showing. We actually did the cracking analysis of the whole system, showing that what they have actually designed for us and provided us was going to crack exactly the way it cracked. It cracked every certain amount of feet, exactly the way that the book will read and the way that ACI will show you. We just show now with analysis that actually that's what they were going to get. Okay? Then the next one, the last one, which I'm going to be talking, is also another very interesting restraint shrinkage cracking. Well, it was all sort of things, but restraint cracking during construction. And this one is actually, as you can see there, I'm not going to get too much in the details, but it's a water filtration, water treatment system. And one of the failures in this design, they didn't have any disruption of continuity of rebar, neither by joints or by, in this case, either by joints or by appropriate detailing. Let's put it that way to avoid the confusion. But in this case, something they did that created a lot of cracking, as many people do, is actually getting to in the lower part of the walls, you have a lot of rebar. But then at some point, they obviously say, well, we are far from the restraint at the bottom, so I'm going to start releasing a lot of that rebar. So what ended up happening is we were very compliant on the part under the about 4 feet there. And then after that, we started seeing wider cracks. Why is that a contractor problem? The design is telling them that actually what they got is working the way they designed it to work. They put more rebar at the bottom, you close the cracks. They space out the rebar at the top, then you get bigger cracks. Why is that a contractor issue? Is there anybody that can tell me that's a contractor issue? Getting cracked? The contractor is not an expert on design. And the contractor doesn't inspect the design, but, that's not a contractor issue. The contractor followed the specs, used the materials specified, used everything approved for construction, built the work. There was no non-compliance. We let the concrete obviously get built. As the concrete started getting more restraint, the cracks started to happen. We got to see our 0.012, 0.014 in some cases. It all vary by the detail I'm going to show you now. So then the other part that we start seeing was we're getting a lot of cracks on this transition zone. That's another detail that I always say is a bad detail. You don't want to be having something extremely stiff and then disconnected by something really loose. Because what's going to happen? The more flexible part versus the rigid, and then the transition is going to have an immediate crack at that location. So what you can see here, I tried to do my best to portray this, but you have here very rigid system. As you can see, you create this is a top view. So you have here a big wall, heavily reinforced. This is a beam, so now you have all the connection there and all the restraints. And all of a sudden, the transition here, look at how it is. You go from being stiff and very heavily reinforced to a zone of very lightly reinforced section. What's going to happen when something wants to crack and obviously have some movement? It's going to crack there. Right? This is expected by design. And then this is another analysis for Calvin, actually. Look at how cool is this one. So this one actually, we went to look at the walls that were showing some, as you can see there, some moisture penetration from one side to the other, so they were not leak free, and we had to do a lot of fixes there. But what do you see there is actually, we went and analyzed exactly the design as provided. And we ended up showing that exactly the design as provided was going to show the crack exactly as we provided. So the contractor provided the cracks that they designed for. Now, the issue is that, as everybody was talking here earlier, the designers don't do that type of analysis before, right? And they don't specify conditions that are going to be, to some extent getting into the behavior of the material and the restraining conditions during construction. Once the building is completed with all the sequence of work, so all of a sudden you create cracking conditions that most likely nobody thought that they would be checked and verified the way we did. But there was a point that we had to actually get into this cracking analysis to show them, we're doing everything you designed. So we needed to check actually we were doing something wrong, and when we did it, we showed. And then you could see here, actually the red points are the red when we actually showing that you have more rebar. So we did a sensitivity analysis. And we show with the sensitivity analysis that if you would go and reduce shrinkage, because there was no shrinkage requirement, by the way. No shrinkage requirement. These were actually for all the people that are in the internal cure concrete. Okay. So we said, okay, we're going to make an assumption this concrete has a certain amount of shrinkage, and then we check the shrinkage. Okay, now we're going to make a reduction and see what happened when you do that reduction. Just to see a sensitivity analysis. What would have been if they would have specified a lower shrinkage? Didn't move much the needle. You want to see how much it moved the needle? About 5%. Not much, right? Then we say, okay, what about, maybe this makes out a lower temperature rise, right? Less heat of hydration, right? So we went and did a modification. We reduced the heat of hydration, and we make it like if we had lower cementitious content with lower heat, and see what happened when you do that, right? Because those are the things that you can control. Then we get about 2%. So the temperature rise of the mix did not move much the needle. The shrinkage did not move the needle. And then we start creating combinations, right? But obviously once we put more rebar, in this case, you could see that all of a sudden we ended up with over 20% here by only doing the rebar, and you get up to 25% improvement as you start combining having low shrinkage, having lower temperature rise, and then having more rebar. All together would have created an improvement, right? But again, the point is that who owns the rebar design? It's not the contractor, right? So we go back to, sometimes we go to these projects, it doesn't matter what you do, you can have the best mix, the low shrinkage mix, the best curing method, go into even internal curing, do everything you can, approve it, right? Make sure that you're within compliance, everything you do, and you're going to get the cracks. But then what comes back is that then that design team needs to understand that there's a responsibility to make sure they understand the service conditions and the construction operations to build the work, so actually they can provide adequate detailing of those designs to make concrete structures that can at least reduce cracking risk or mitigate the cracking better, because obviously the contractor in that case is not going to be the only solution. So with that, again, this is what you guys should take from here. You can do your best effort. The designer can do their best they can. You can have the best mix, and the client can have the best amount of money to actually build the work. But you have to come to that happy medium. If you want to be only on one side of the equation, you're not going to be able to be successful. And like I said before, you can control, mitigate, and reduce cracking. But if you want to get into crack-free structures, you need to then obviously make sure that you have the right specifications, design, cost, schedule, materials, and construction methods to actually be able to reduce the crack significantly, to maybe get crack-free. But again, even post-tension structures are going to get cracks.